Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're happy to have as our speaker today Samir Kuler from the University of Maryland. Samir finished his PhD at Cornell in 1990 with Vijay Vazirani. Then he was a postdoc at UMIAX at Maryland, and since then he's been on the faculty there, the computer science department. Has written many papers, made fundamental contributions to theory of algorithms, and he'll talk today on algorithms for data storage and migration.
Thanks, Ifi. So most of this is joint work with two PhD students, Kim and Justin Wan, and there are parts of it that are not. And so I'm going to, in the end, going to give you all the papers that went into the talk that I'm going to talk about. So the work was originally motivated by trying to deal with designing algorithms for storing large volumes of data on kind of a parallel disk system. So most of these disk systems are composed of, say, hundreds of disks. And our main application was video on demand server. So you have a lot of multimedia data that you're storing on disks. So the data is sort of write once. You store the data and then you're streaming it to clients. It's not as if the data itself is being changed all the time. And the disk system itself has several constraints that I'm going to describe in a minute. And to sort of handle those constraints, we may have to replicate data. And so the data needs to be replicated both for fault tolerance purposes, but also more importantly to deal with high demand for some data objects. So we're going to discuss sort of problems dealing with how to compute something called a data layout, and then I'm going to talk a little bit about, as the demand for this data changes over time, how can we adjust the layout to deal with the new demand patterns. So more formally, what is a data layout? Let's say I have a collection of disks, and each disk is specified by two important parameters. One is simply how much data can I store on this disk. So I'm going to sort of assume for simplicity right now that each data object, A, B, C, D, etc., these are data objects, they have roughly the same size. So just imagine this is a file which is, say, 1 gigabyte in size, and each disk has a certain capacity in terms of how much data it can store. In addition, because this disk is streaming real-time data to the clients, there is also a second component which is the load capacity, as to how many clients can be served from this disk at any point of time. So each disk comes with an upper bound on the load capacity. And now for these different data objects, I have non-uniform demands. So for example, maybe item A is extremely popular and there's a demand of 20 clients who are interested in item A, B and C are not popular at all, and so on. So notice that even though we have, say, one copy of item A, because of the load capacity, we cannot handle all of the demand for item A, and we may have to make multiple copies. And the main question is sort of for every data object, I have to decide how many copies to create, and more importantly, which disks to store them on, because I don't want to put too many things in high demand on the same device. Right? So let's just give you a very simple example to illustrate the problem. So here I have two disks.
And everything is known in advance.
For now, let's assume everything is known in advance. So for example, you might say some vendor decides or has some advanced information for what demand they're going to expect, and they ask you, how should I lay out the data to maximize the utilization of the system? If I create lots of copies of unpopular items, that's not going to maximize the utility of the system. So in this simple example, I have shown you two disks, and each disk can handle, say, 100 units of load, but can only store two objects. So the total capacity of the system is 200 clearly. Now let's say that our total demand is also 200, so there are 200 customers interested in the data. So suppose we chose this layout where I put A and B on the first disk and C and D on the second disk. Notice that the total demand for C and D is 80, so this disk is essentially underutilized. It had a capacity of 100, but I'm only loading it to 80 units of load. And this disk, the total demand for these two objects A and B is 120, but I cannot assign all of that load to that disk. So I said assign 90 customers for A and 10 customers for B, and the remaining 20 customers for A are essentially told, sorry, you cannot get what you want. Okay? Even though there was load capacity available in this system, this disk doesn't have space to store a copy of data object A. Okay? So is the problem clear? And we're simply trying to maximize how many customers can be assigned to the data they want to be assigned to. So in this placement, for example, the total demand satisfied is 180. Turns out that's actually not an optimal solution. So for example, if I just dropped item B completely, moved item C to the first disk and made another copy of item A, now actually you can increase the utilization of the system. So in this layout, I have 2 copies of A, and these numbers 50 and 60 tell you how I have split the demand for A, right? So 50 customers for A are being served from that copy, the remaining 60 from this copy, and I have now satisfied 190 customers out of the 200. And there's in fact no solution that satisfies all of the 200 customers here. Okay? So in general, the data layout problem could be described as you have n disks. Each disk has storage capacity K and load capacity L. And I'm going to assume that the total number of data objects doesn't exceed n times K. Notice that that is an upper bound on how much data we can ever store, right? If I have n disks and each disk can store K objects, I can never expect to store more than n times K volume of data. So that's an upper bound on the total volume of data. And the total demand that a system can handle is at most n times L, because I have n disks and each one can handle L. So for now I'm going to assume that all the disks are identical, even though many of our results do extend to non-identical disk systems where this disks in the system can have different capabilities, different capacities, different load capacities, different storage capacities, and so on. And the point is that because the demand is imbalanced, some of the demand cannot be satisfied. So this example is again very trivial. It just says that even in the simple case where, let's say I have 2 disks, each can only store 1 object, the problem is that if object A is in very high demand and has demand 150, object B is in very low demand, has demand 50, once I put a copy of A on the first disk, essentially now I can either store A or B on the second disk, and in either case I can only assign 50 customers there. Right? So out of the 200 customers, I have to leave out 50 customers for A or B. So in fact, when each disk can only store 1 object, a greedy algorithm gives you an optimal solution, but what we show is that the problem becomes NP hard even when each disk has capacity just 2. So it's NP hard for any fixed value K greater than or equal to 2, even for identical storage systems. By identical, I mean homogeneous storage systems where all the disks are identical. So this problem had been studied before, and there was a very nice and elegant algorithm called the sliding window algorithm given by Khanna and Tamir. And essentially our work starts off from there, and we give a certain analysis of their algorithm that I'm going to describe to you. And so while we were studying the algorithm, we noticed that actually you could improve the running time of the algorithm to essentially n log n from the original running time, which was quadratic, which was given in their paper. This is sort of the main thing that we're going to focus on, which is a tight upper and lower bound on the number of requests that can always be served for any input instance. So essentially I'm assuming that I have n times K data objects, and I have n times L customers, but we know that there are storage patterns where we are forced to drop certain customers. We cannot handle the whole demand. But what we're going to focus on is proving bounds, which say something like a certain fraction of the demand can always be assigned regardless of what the demand was. Okay?
What is the M?
So n is the number of disks and m is the number of data objects, the number of movies. Okay? And we also developed a polynomial time approximation scheme, which was one of the main open questions left in their paper. But this algorithm is very complicated and it's not practical at all, so I'm not really going to talk about it. And finally we extend several of these results to non-uniform disk systems where the disk system is composed of different kinds of disks. The only assumption we make is that sort of as disk technology improves, that not only the disks sort of can store more data, but they also get faster, so they can handle more demand. If the disks are completely arbitrary, then I don't know how to extend the results that I'm going to talk about. Questions? No? Okay, so let me first start off by describing the Khanna and Tamir algorithm. It's a very, very simple algorithm. And the main idea behind that algorithm is to keep a sorted list of movies in increasing order of demand. Okay? And then we are going to sort of start allocating which movies go together on a disk by sliding a certain window, and that window is going to start from the left. And this is a little bit counterintuitive because most people seem to think that, well, I should start off by assigning the more popular movies first, and that's not what this algorithm is sort of doing. Okay? But I'm going to explain this algorithm in a second by an example. So let me sort of just try to focus on the main thing that we're trying to do, and then we can come back to the slide, and once I've shown you the example, it'll become completely clear as to what's happening. So the goal will be to try to take a window of size k, which specifies sort of how many movies I can store on a disk, and we're sort of picking up the first disk and trying to decide which subset of movies to put on that disk. And I'm going to slide a window of size k until I find a consecutive subset of k movies whose total demand is at least L. Right? So let's go to the example, and that will make the algorithm completely clear. So in this example, we have 3 disks. So n is 3. Each disk can store 2 objects, k is 2. And I'm going to assume that the load capacity is 16. So 16 customers can be assigned to each disk. Now here I have color coded the different data objects. So I have 6 movies or 6 data objects. The first 4 of them have demand 6, and the last 2 have demand 12 each, right? So the total demand in fact should be something like 48, which is the total capacity of the system, right? I have 3 disks, each one can satisfy a load of 16 units. Now let's try to decide which 2 objects should go on the first disk. I'm going to start this window of size 2 and look at the total demand of the first 2 items. If their demand is at least L, we'll say, okay, let's put them on the first disk. But in this case, the demand for the first 2 items is only 12, right? Which is less than the load capacity 16. So if I put this pink and this yellow item on the disk together, the disk would be full in terms of how much it stores, but it will be underutilized in terms of its capacity. So then we're going to start sliding the window. And the first place this window will stop is here, because these 2 are the first consecutive pair of items whose total demand is at least L. So their demand is in fact more than L, it's 18. So what I'm going to do is I'm going to pack these 2 objects, the purple one and I guess the light blue one, on the first disk. All 6 customers for that object will be assigned here, and 10 out of 12 customers for that object will be assigned to this disk. Now there will be still 2 customers left over which were not assigned to anything, which were interested in this object, and I'm going to break off those 2 customers and reinsert them into the sorted list. Okay? So at all times we're simply maintaining the sorted list of customers who haven't been assigned yet, and then I'm going to pick up the next disk and try to assign them. Okay? And so in the next step, when I fill the second disk, these 2 are gone now, and this one left behind a piece of size 2 that got reinserted in the beginning of the list, and this item, green item of size 6, will merge with this blue item of size 12, and that demand is again at least 16, and again a little dark blue piece will be broken off and stored back in the beginning of the list, and in the end these 2 items will be put on the last disk, because in the end there's no option, there's no pair of items whose demand is at least L, so I'll simply take the best set and put them there. Now notice that the total number of requests that were served here out of the 48 requests that we had was 44. So we actually served 91% of our customers. Any questions about the algorithm itself? So have a good time to stop and clarify any doubts, because things will get more complicated in trying to analyze it. Question?
What happens if we can't locate the window in the initial iterations itself? So each of them had a demand of 1. If each of those pink, yellow, if everything was 1, you can't identify a window of.
Right, the window will slide all the way to the right hand and simply grab the most popular group of size k, which is the biggest k items. Question?
You had earlier motivating this, you were talking about not only this question of handling the demand, but also redundancy and error fault tolerance.
Yes.
Are you forgetting about fault tolerance?
For now, yes. So you're absolutely right. We're not really controlling how many copies get created. I was just sort of saying that there are multiple reasons why people may want to have multiple copies of data, and here the one that I'm focusing on is actually just in trying to handle the demand. But fault tolerance is sort of a standard reason why people want to replicate data. Okay, so now, so what are we? So any questions about the algorithm? So that was sort of the algorithm. Let's talk a little bit about what we can prove about the algorithm. So what is our main goal? Our main goal is to try to show that the total number of requests served, in this case which was 91%, this is pretty high. And this is pretty high regardless of what the demand for the data was. And in fact, I'm going to show you a certain function. Let's just jump to the function. So the main theorem is that the total demand that is satisfied, or the fraction of demand that is satisfied, is at least this value. So the only thing it depends on is k, which is the size of the disk. And notice that this function approaches 1 pretty rapidly. So when k is 1, this function is 3/4. So what it says is that when all disks have storage capacity 1, at least 75% of the demand can be handled, no matter how the demand was.
U is the demand, the total demand of the.
U is the unsatisfied part, and S is the satisfied part. So U plus S is the whole thing, the total number of customers, and S is the satisfied customers. So what I'm saying is that the function's already.
U is huge.
Oh, so we assume that the total number of customers cannot be more than the capacity of the system, which was n times L. Right? Because essentially, if you can't handle the demand, you sort of need to buy more hardware. But the point is that, of course, you can always throw more hardware and solve the problem that way. But with existing hardware, the point is that even if your total number of customers doesn't exceed the system's capacity, because of the skewness in demand, we can't handle all the demand. Right? And what I'm trying to argue is that for this algorithm, this function tells me that how much demand I can satisfy. What's not obvious is that actually this function is the best possible. So what we can show is that there are examples that say that basically that there are input distributions for which no matter how you do the layout, even the optimal layout, cannot guarantee handling more than this demand. Okay, so that part is a bit surprising, that this function is in fact the best possible function in that sense. So what it may be is that the problem in general is NP hard. So it may be that I'm not saying that we are finding the optimal solution. So there may be specific instances for which the optimal solution does better than what the sliding window algorithm does. But there is no general algorithm that can claim a better bound over all input distributions, because there are input distributions for which no matter how you do the layout, you're going to lose that much. So to illustrate the point, let's go back to the very simple example I showed you when k was 1 with just two objects A and B. I had two disks, each disk could handle 100 units of demand. If the demand for object A is 150 and the demand for object B is only 50, after you've put one copy of A on the first disk, on the second disk you have a choice of either putting 50 customers for A or 50 customers for B. No matter what you do, you're only going to handle 150 customers out of the 200, which is exactly 3/4, which is what this function tells you. When k is 1, it's 3/4. But this improves very rapidly. This function goes to 1 very rapidly as k gets larger and larger.
What about the optimum of the given input compared to the optimum of the traditional approximation factor?
So we have a polynomial approximation scheme.
Oh, yeah.
Yeah. Okay.
But
So the polynomial
what
approximation,
is the approximation factor of this algorithm?
it's the same actually. So, and we use essentially this algorithm for even the polynomial approximation scheme. So if the disks are very big, k is very big, then this loss term is essentially approaching 0, and then you can essentially use this algorithm for very large k. And the problem is sort of hard when k is constant. And for k is constant, we design a separate dynamic programming based algorithm that gives you an approximation scheme, but the running time of that algorithm is huge. It's not even comparable to this algorithm, so it's completely impractical. Question?
So just to be clear, in this sliding window algorithm, you could fractionally divide the
Customers, that's right.
And when you apply this algorithm to your problem, will you still be allowed fractional solutions like this, or will you?
So when we say we fragment things, essentially what's happening is that, let's say there was a new movie called Cars that came out, and 1,000 customers were interested in Cars. If your disk had capacity 750, basically when we break the item, we're not breaking the movie, we're just putting a copy of Cars on the first disk, 750 customers assigned there, the remaining 250 customers will be now have to be assigned to a second copy of cars. So the moment I break something, I have to store a second copy. Question?
So under the assumption that the capacity, suppose, is less than what the demand is, now you made the assumption that capacity, demand is at most capacity.
Right.
So if you remove that assumption, does this algorithm give the same?
So I think in that case, what one could do is just take the most popular items and take the demand of those which doesn't exceed the capacity of the system and run it, and I think that should work, but I'm not 100% sure about that for sure.
Might be that if you do better, it might be that if you take the most popular ones, you will not pay it.
Yes, yes, but I think this bound will still work, I suspect, but maybe you can do better, you're right. Okay, so let's go back and at least try to understand how we can go about proving that bound that I just described. So for proving that bound, to do the analysis, we have to look at once the algorithm terminates, how many disks there are of this type which are load saturated. So we refer to NL as the number of load saturated disks where the actual load is exactly L, which is the capacity or the load capacity of the disk, and then the remaining disks will be referred to as storage capacity saturated disks where their load could be strictly less than S, and they are referred to NS. And so NL plus NS is simply the total number of disks in the system. So going back to this example, notice that out of 3 disks, 2 of them are load saturated, and the last one is not load saturated. The load is less than the total load capacity of the disk, but it's storage saturated, namely it's storing K objects. Because if this disk wasn't storing K objects, and if anything was left out, I can add that to this disk because it has available load capacity and storage capacity. And now what is this term little c? Out of all the disks here that are storage saturated and their demand is less than L, C is defined by the disk with lowest load. In this case there was only one disk, so the load is 12, and it's the ratio of the load on the disk to the total capacity of the system. So this disk is 3/4 loaded basically, and so C is simply the smallest over that set of disks. Okay, and essentially now to do the analysis we have to prove some bounds on these how many unserved requests I have and how many served requests I have. And the way we prove these bounds is the following. So the main thing we are going to be able to argue is that the number of data items that got left out and were not stored in the end. So notice that in this example these 2 items got left out, 2 movies got left out with 2 customers each. The number of such items that got left out can be upper bounded by NL, which is the number of load saturated disks. So it wasn't a coincidence here that I had only 2 things left out, because in fact I had 2 load saturated disks. So what I'm claiming is the number of movies left out here doesn't exceed this parameter NL. So NL is an upper bound on that value. And the remaining CL over K, we are saying that is an upper bound of how many customers each of those movies might have had that were left out. Okay, so in this case again out of this movie there were 2 customers left out, right? And notice that how much is CL over K here. So C times L is simply the load on this disk, which is 12. This disk had 2 movies. If I divide that by K, which is 2, I get 2. Actually I divide 12 by 2, I get 6. So what I'm saying is that the total number of customers interested in this movie cannot ever exceed 6. Okay, and that makes sense, because otherwise I would have stored this object on the disk and not what I stored, because in the end it boils down to a greedy algorithm, because once I'm producing non-load saturated disks, I'm simply picking the ones with highest demand and storing those data items on the disk. So, and the product of those 2 certainly gives me an upper bound on what I left out, because I'm bounding how many movies got left out and I'm bounding how many customers might be interested in each of the movies that were left out. So that's sort of the main thing that one needs to prove in making this argument go through. The lemma 2 is actually very straightforward, because all I'm saying is that the number of unserved requests is at most this quantity, right? And if you look at carefully as to what this is saying, is simply a trivial bound on how many things were left out, because I produced a whole bunch of load saturated disks, and how much demand wasn't served, it cannot exceed NS times how much I left out on each of those disks. So that's a completely trivial bound. So if you miss that, don't worry, you can easily work it out in 3 seconds. And this again bound is very trivial. It just says how many requests did I served. Well, I certainly served L times NL requests because they were being served on the load saturated disk, and each of the storage saturated disks served at least C times L demand. So the product of that this just gives me how much demand I served, right? So the only tricky thing is actually proving lemma 1, and then the rest is just very simple to derive that function. Okay, so what's the idea behind the proof of lemma 1? How am I going to claim that the number of movies that are not served is at most NL, right? To prove this, we have to prove the following claim. We're going to claim that if you think about the load saturated disks that are produced in the beginning of the algorithm, the disk that had load exactly L, the claim is that each of those disks must have exactly K objects on it. Okay? So again, it wasn't a coincidence in this example that those disks had exactly 2 objects on them. It says that each of those load saturated disks have exactly K movies in it. Otherwise, in fact, we can prove that all the requests were served and nothing got left out at all. So you've satisfied 100% of the demand. So if anything ever got left out, it must have been that each of those load saturated disks had K objects on them. And what was happening at every step, we were breaking one object for each of those load saturated disks, and that was sort of generating extra objects that we had to handle. And we created exactly NL extra objects that we have to handle. So and essentially NL extra objects may not be stored, because every disk is storing K things. So certainly the ones which are not load saturated but storage saturated are storing K objects. But the point is that even the load saturated disks are storing K objects. So where did all these objects come from? Well, at most NL objects could have been left out then, because otherwise I would just run out of objects. Okay? Does somebody see how we might prove this claim? Why is it that the load saturated disks have to have exactly K movies in them? What happens if they have strictly less than K?
The beginning of the algorithm, the definition was that you look
For K, yes. Right. Okay.
So this point, so I wasn't completely honest when I described the algorithm. So if you look at the first group of K things in the list, now let's say their demand is bigger than L, okay? But maybe all of them have very high demand, okay? So what might be is that even if you drop the biggest data object completely, maybe still the demand is more than L, right? I was claiming that I can break off that one last piece and store K items that have demand exactly L. That may not even be possible. Let's say K is 1. So I only want to store one object on this disk, and the first thing has demand more than L, right? Or I want to store 2 objects, and the first one alone has demand more than L, right? When I take the first 2, the demand is very high, but even if I drop the second one completely, the demand is still more than L.
Since you're sorting in the total average load is L.
In a sense, so what's going to happen is that if you look at the first, say, P objects, which are less than K, and even their load is at least L, then what's happening is that suppose I stored K minus 1 objects in the first disk, and then I broke off a piece and put it back, that means we didn't slide the window at all. In fact, the first K minus 1 things gave it to me, and then this one broken off piece together with the next K minus 1 will again form a load saturated disk, because in fact the first K minus 1 formed a load saturated disk. So that way you can argue that everything would in fact get specced. Okay? We'll produce load saturated disks all the way to the end until I run out of items. Okay. So this I've already talked about. So now once you put those two lemmas together, it's just a question of a little bit of algebra, a little bit of optimization, and eventually that bound pops out. I have sort of no intuitive way to explain why we got that bound beyond just doing the calculations. So how much is the wastage? So we actually now in this plot the wastage. So the wastage actually is this curve here. So the wastage at K equals 1 starts out as being 25% and then very rapidly goes to 0. So by the time you're up to, storage capacity of 10, you're already having very, very low wastage, maybe no more than 5% or something. And this last curve, bottom curve here, tells you how much wastage we got when we implemented this algorithm and tried it on different demand pattern. So the algorithm is already doing better than what the worst case bound seems to suggest. Okay. So the next part of the talk deals with this issue about when the demand itself is changing over time. So we take some expected demand pattern and use that to compute a layout. Once I have found a layout, and let's say the demand changes, right? So some data objects that we thought were going to be extremely popular and we created lots of copies for them turned out to be not so popular, and other objects that were in very low demand and I only had one copy maybe became very popular. So how can we sort of convert an existing layout to a new desired layout? So that's sort of the main focus of this talk that we're going to call data migration. So you have some current layout which was computed perhaps by using the sliding window algorithm or by some other algorithm, and you want to have a new layout. We want to convert this layout to that layout. Okay. So we have to talk a little bit about the underlying model as to what's happening when this data is being moved around. So we assume that any pair of disks can transfer data between each other, and in fact we already assume that all data objects are the same size. So whether if I want to transfer object A from one disk to another disk, it takes the same amount of time. But so essentially the model says that the disks are connected on some kind of network, and we can pick a pairing of the disks or a matching and then transfer data on that matching, and the network can support those transfers. We also have another model where we limit the amount of communication the network can support. So the network may be able to support any matching, but a matching of some size. So it cannot transfer more than 20 transfers happening at the same time. So the algorithms even work for that model. And so there are two models, a half duplex model and a full duplex model. In the half duplex model, we assume that one disk can transfer data along this matching edge to another disk. In the full duplex model, they can essentially each disk can be the sender or the recipient of a data object. Okay. So there was another paper that by actually Anna Carlin at University of Washington and some of her students that looked at this problem, but their formulation of the problem was a little bit different. So let me talk a little bit about that. So the way they defined the data migration problem, it was you're given a fixed transfer graph. So each node in this transfer graph refers to a disk, and a directed edge refers to some data object that you want to move from this disk to that disk. Okay? So you might have some data stored, and you might say, well, I want to move this guy here and I want to move that guy here, and so on. So you set up sort of a directed graph which tells you what are the transfers you want to do, and they essentially use the same communication model, which is the matching based model, where in every round you can transfer a matching, and our goal is to minimize the number of rounds or the time taken to do all the transfers. So that now translates simply to an edge coloring problem, because you simply want to give an edge coloring to every edge, and all the red edges form a matching, the blue edges form a matching, and so on. You want to minimize the number of colors you used. So again, that problem for multigraphs and simple graphs is NP hard, but there are sort of good approximation algorithms known for that problem. And the main thing that they dealt with was space constraints, namely that this disk may have 3 objects initially, and in the end it may have 3 objects, but they never want
1.1 approximation. I mean,
for edge coloring,
so for edge coloring.
for multigraphs.
Multigraph.
Edge coloring multigraphs.
So 1.1 is the best known approximation for edge coloring for multigraphs.
Actually, it may have been improved slightly. So there was a paper by Hochbaum and Nishizeki several years ago, which gave this bound, and I think in sort of a couple of 2-3 years ago there was some improvement slightly, but then they sacrificed on the additive term. So the bound is actually 1 plus 1 over k times opt plus some other additive term which depends on k. So the additive term grows up as you try to improve that.
Way behind on those, but somehow. So the first things that you do is like Shannon's theorem, which will
Like the
1.5.
give you 1.5.
or delta plus mu, right? And Weising's theorem, which is only for simple graphs. Yeah.
Right, and then the improvements are by what? By looking
No,
How do you do betas and
delta plus mu and 1.5.
so those are bounds compared to certain lower bounds, not against the optimum solution. So there's the general 1.5 thing you mentioned is just 1.5 times the maximum degree of any node. They're not utilizing any other lower bounds. Yeah, so actually I tried reading the Heuristic paper, but it's very long and complicated. They're trying to develop some new lower bounds by the idea of looking at certain subgraphs and arguing that on those subgraphs each color class must form a matching.
Normally,
Odd graphs.
That's right. So I think they're using the same insight, but they only look at perhaps triangles. Yes, not like arbitrary size, right? So in their model, once a transfer graph has been specified, it becomes exactly an edge coloring problem. Okay, so our formulation of the problem itself is a little bit different. So our first question is, how do I even find a transfer graph? And the second point I want to make is that actually the data migration time can be reduced via this idea of cloning. So let me just talk about a simple example. So let's say this was my initial layout, this was my target layout. Now notice that I want to have this disk get item 1. For item 1 there is only one source, disk 1. I want this disk to get item 2. For item 2 there are actually two sources, those two. So this is one possible transfer graph that might get created, which says that disk 1 will send item 1 to disk 3 and disk 1 will also send item 2 to disk 4, right? But notice that in fact had I chosen a different transfer graph, we could have done better. This would take you at least 2 rounds of communication, whereas this can be done in 1 round. Okay? So the point is that I shouldn't just make some ad hoc assumption about who's going to send the data to somebody who needs the data, because multiple people may have the data. The second point I want to make is this idea of cloning. Well, let's say one disk has item 1 and then I want to have lots and lots of copies of item 1. In their model actually they would set up a transfer edge from that source to all of these disks, giving this node a very high out degree, something like that. Whereas you can actually do the following. Once disk 1 sends item 1 to some other disk, while it's sending item 1 to some other disk, that one can start creating new copies of the item. So in fact in log of the number of copies you want to create, you can actually generate all those copies as opposed to using only one original source for the item. So we don't want to set up a particular transfer graph. The way I'm going to define the problem is that we have certain source sets and certain target sets. So SI is simply a set of source disks that initially have item I, and TI is a set of target disks that need item I but don't have it initially. So for example here, for item 1, which are the sources for item 1? Disks 2, 3 and 4 have item 1. So S1 consists of the set 2, 3, 4 that's marked in this red rectangle. Now what is the target set for item 1? It's those disks that don't have item 1 that need item 1, which is namely just disk 5. So the target set for item 1 is just disk 5 there. Okay? So we have the source sets and target sets. And the goal is to do these transfers where I minimize the number of rounds, and what you're allowed to do in every round is simply pick a matching and do the transfers of items on that matching. Okay. So the problem again, since it generalizes edge coloring, is NP hard. So the first algorithm that we came up with was 9.5 approximation. So this bound 9.5 is pretty big, and we've been working since then trying to improve it, and so now we have it down to 6.5 actually. But anyway, it was the first constant approximation for this problem. So in joint work with Kim and Nazaraks Malakian in a paper that we presented at this year's Approx, we have improved the bound to 6.5. And we also now looked at the full duplex model where each disk can receive an item and send an item at the same time, and for that in fact we can show that we have an upper bound of 4 approximation. Okay. So now sort of again a good time to stop and ask questions and clarify doubts about the definition of the problem. Then I can spend a few minutes talking about some of the ideas that are needed. So the 9.5 algorithm is actually very complicated. So I'm going to just take a very simple case and describe how to solve that case.
So just for constant approximation, you make
They're only about the maximum degree, maybe, because
well, we don't even have a transfer graph. Remember that.
yeah, no, I'm saying that
you can try to choose the transfer graph.
That minimizes.
minimize the maximum degree.
Yes.
Up to a constant vector, that's the same.
That's right. Well, no, because of the cloning properties. Yeah, cloning may let you generate lots of copies, and that approach won't let you do that. Exactly. Question?
So in your model you have source nodes and target nodes.
Right.
And you're moving from one to the other.
Yes.
is it clear that it wouldn't help to in some way have like a temporary node where so you're sending something in order to maximize this this cloning process and then later go back and maybe put something.
So I believe that if you allow yourself to use extra copies, you should be able to reduce the number of rounds required, and essentially you're doing some redundant transfers, right? So our algorithms actually, the only transfers they will do are from the source set to the target. So the total number of transfers that we do is optimal. You cannot reduce that, okay? So we will not even do one single redundant transfer, and we're actually comparing to an op that can do whatever it wants. So the optimal solution might use bypass nodes or whatever it wants, and that's fine. Okay, question?
Do you allow the source? So after the first round, one more additional node, the set of sources increases. So do you actually take that into account?
Yes, yes.
So does the algorithm actually use the additional sources, or it just?
So without that, this cloning will be a problem, because the optimum solution could do much better than you could do if you don't allow that. Right? But his point was that maybe you can do better using bypass nodes, and I completely agree that I believe you can do better. So, but our algorithm will not use that, whereas the optimum has the freedom to use that. Okay, so let's talk about this very simple case, because it at least illustrates one of the central ideas behind the algorithm. So here I'm going to assume that every data item in fact has only one distinct source. So that solves the problem of which source you're going to use. But the target sets are completely arbitrary, and I'm going to just show you how to get a very simple 4 approximation. So in that much time, I think this is sort of what I can cover easily. So let's talk a little bit about the simple case. So here the sources are unique and distinct. So every item has only one source, and it's different from another item source, right? So that's the source set for item 1, that's the source set for item 2, source set for item 3, and so on. But the target sets are completely arbitrary. I have no assumptions on the structure of the target sets. So these 3 disks are interested in item 1, these set of disks are interested in item 2, and so on. So our first thing that we're going to do is we're going to try to select some representatives for every item. Think of these representatives as some kind of helper sets or helper nodes. If some item has a very big target set, right? So suppose you have one source for item 3 and the target set is simply huge, then you kind of want to pick a bigger helper set that's going to help you propagate this information to those disks that need that item. So these representative sets are going to be subsets of the target sets, and they'll be disjoint from one another, but they'll also be big enough. And I have to sort of be more formal about what I mean by all these terms. And the high level idea is going to be simply to send the data to these representatives, and then we'll create a transfer graph from those representatives to the remaining disks, and then we can find a schedule using edge coloring. Okay?
These representatives you will
Send directly from the source, say,
We will use cloning.
use cloning.
But also,
type the representative.
that's right, exactly. Yeah. So it's a very, very simple problem. So now I just wanted to tell you how to choose the sizes appropriately. So here beta is the maximum number of items any disk needs. Okay. So let's pick some disk. How many items does that disk want? Anyone? How many items does that disk need? Just one item. Item 4. It's in the target set for only one set. This disk, on the other hand, wants more items. This disk wants at least 3 items, right? It wants item 6, item 3, and item 4. So beta is the maximum number of items any disk needs. So in this case, in this example, beta is 3. The maximum number of items any disk needs is 3. And in fact, notice that beta is also a lower bound on the optimum solution, because this disk needs 3 items. It's going to take you at least 3 rounds to deliver the item to the disk, because in every round you can only get one new item. So I'm going to define the size of the helper sets as the floor of the target set divided by beta. And then we're going to choose these representative or helper sets, and they're all disjoint. So the green sets here are all my helper sets. And notice that in fact the helper set for item 4, which is this green set, in this case it has 3 disks in it, is a subset of the target set of item 4. So these disks only get that item because they were already in the target set for that item. Okay? So a helper set is only a helper set for those items that it already wants. And so these helper sets have to be chosen carefully so that they are all disjoint and they all have to be of this size. So in this case, let's look at T5. T5 is 1, 2, 3, 4, 5 disks. Beta is 3. The floor of 5 over 3 is just 1. So in this case, that helper set has size only 1. But there is some bigger target sets have larger helper sets and so on. And how are we going to pick these? We just have to use network flow appropriately to make this choice. So basically, we're going to build a flow network with a source and a sink. There's a node here that represents the disks. It gets a flow of 1 unit, and these nodes here represent data items, and the capacity of this edge represents how large is the helper set for that data item. I make that the capacity of this edge, and in this network I'm looking for a max flow that saturates all of these edges. And we can show that a max flow exists that saturates these edges because we can show there's a fractional flow that satisfies all these capacities, and so there must be an integral flow because the capacities are all integral. Yes, exactly. It's nothing else, right? So that's how we're going to choose the representatives, and then we're going to somehow transfer the data from the representatives to this representative set, and then use cloning within the representative sets to propagate the item. And then in the end, I'm going to set up a new transfer graph where I'm going to transfer data from these representative sets to other disks in the target set. And notice that the ratio of these two was chosen carefully. It's roughly beta. So in fact, we can show that the out degree of each of these nodes is something like beta minus 1. And beta is already a lower bound of the optimum solution. So, and when I'm going to apply edge coloring on this whole transfer graph in the end, the number of colors I'm going to use is going to depend on this degree of this graph that I'm going to set up, right? And the degree depends now on two quantities. Notice that some nodes that were source sets for some items could also be in the helper sets for some other item. So they have to sort of deal with the item for which they were the source and also an item for which they got chosen as a helper set. So finally, when you put everything together and you use sort of the multi-graph result that Noga had mentioned earlier, and you find an edge coloring where the number of colors used is the maximum degree plus the multiplicity, putting all that together actually gives you roughly like a 4 approximation. So where is this 4 coming from? We sort of spend that many rounds to move the data from the source to the representatives, and then we have to sort of count how many rounds we take from moving the data from the representatives to the remaining disks and apply the appropriate edge coloring bound, and then that gives us the 4 approximation.
So Ri is this Ti over beta, or?
Ri is Ti over beta.
And you use that log of Ti is also a lower bound.
That's right, because I have to generate that many copies of the atom. Yeah. So those are the only 2 lower bounds being used here. Question?
The representative sets, they can't overlap, right?
They are disjoint in a disjoint way.
So is it possible that you're stuck not being able to find a large enough set of representatives because the T sub i's all intersect?
Yes. But so there are ways to improve this algorithm. For example, if you allowed some kind of limited overlap between the helper sets, we can use some tricks like that to improve the bound further. So we actually had a bound of 8 using that idea that it's okay for helper sets to overlap so long as each node doesn't belong to too many helper sets. But then by using a different approach, we were able to get a bound of 6.5, the one I mentioned. So that idea actually in the end didn't lead to the best bound. So, but now we're trying to use that idea again on the 6.5 algorithm. So I think eventually this problem will have a 3 approximation or something like that by using some combination of the different ideas.
Is it hard to approximate also? So there is a
Oh, I mean whether it's it's certainly very hard. It generalizes edge coloring.
hard even to approximate.
Better than something?
Yeah, well, edge coloring is hard for 3. So you could say that 4/3 is hard or something.
Yes, but that's about it. We don't have any better lower bounds for this problem than any bound for edge coloring. So what happens in the general case? So where the source sets and target sets are completely arbitrary. So this is a little bit tricky, and the reason is that we lose that lower bound. Earlier on we used the fact that log of the size of the target set was a lower bound, and that was because we had only one copy initially and we had to generate lots of copies in the end. But in fact, look at this example. So here the source sets for all 6 items are this group of identical disks. So all these disks have all the items numbered 1 through 6, but the target sets are all disjoint. Okay, so this is the target set for item 1, target set for item 2, target set for item 3, and so on, right? Now I can't argue that log ti alone is a lower bound in the optimum solution, because maybe the optimum solution takes this whole source set and in one round sends the data to that whole target set if si and ti have the same size. So all we can claim is that this is the lower bound. But on this example, every disk only belongs to one target set, so even our lower bound of beta is not very useful. So the problem is a little bit more complicated, because the best solution for this still needs log n rounds. And the optimum solution, what it does is it moves item 1 from this disk to one person there, item 2 from a disk here to one node there, and so on. That takes one round, and after that in log of ti rounds you can complete by cloning you can complete the schedule. Okay. So for that we have to develop a new lower bound, and that new lower bound is a little bit hard to explain, but maybe in few words I can just say what's going on. So here we are making a flow network where here I have a node for every data item. Here there's a capacity of the size of the helper set, the representative set, and we kind of know that we have to create at least that many copies of each object. In fact, I could even put in ti over here, because I know eventually I have to create that many new copies of that object. The question is, where are those copies going to come from? So for every disk I'm going to create lots of copies, lots of nodes for the disk. How many? M nodes. And the capacity of these edges is intuitively trying to capture the following property. It says that if at time I transfer data from this disk to some other disk, how many copies might this create in the future? Right? If I is very close to M, you can't create too many copies in the future. So suppose I tell you that I'm trying to argue that I need at least 3 rounds to do this transfer. Whatever gets moved to the last round can never generate any new copies. Whatever gets moved to the second last round can only generate, say, 1 extra copy. But things that got moved early on may be able to generate lots of copies. So essentially what we're trying to argue is that this capacity is sort of an upper bound on how many copies might ever get created from this copy that was moved at a certain time. But we know that we need a certain number of copies for each of those data items. So I'm going to essentially plug in a value for M, say equals 1, 2, 3, 4, 5, and so on, and try to find a max flow here where these edges are saturated. If you can't find a max flow that saturates these edges, I'm going to increase that M. And I'm going to argue that whatever M you end up with is a lower bound of the optimum solution, and we're actually going to use that lower bound and this flow computed here in the algorithm. So the actual algorithm is a bit more complicated, and you have to use, if you're familiar with the generalized assignment problem, you have to use techniques from the Schmois-Tardo generalized assignment problem paper to come up with a schedule after you find the appropriate max flow here. So this is actually, maybe I just talk a couple of minutes. So we actually also compared our algorithm to several different heuristics. So the first heuristic is actually based on the idea that Noga mentioned right in the beginning, which is that I want to create a transfer graph where I minimize the maximum degree of any node, except that you don't use any newly created copies as additional sources. So that was one of the heuristics we tried. So let me skip over the example, it's not very interesting, I think. And then a second heuristic we tried was using matchings. So basically what we are saying here is that you can build a transfer graph where an edge UV exists as long as U has some item that V might need, right? It says that I have something interesting to give you, find a maximum matching in this transfer graph, move those items, and then update your source and target sets because there's a new source, and then compute a matching again and so on. So in practice this algorithm does extremely well. Okay, it's one of the best heuristics that we found. Of course there are situations where this algorithm does really badly and it doesn't give you a constant approximation, but in practice we found that this was one of the best algorithms. So let me just show you a little bit about the performance of these algorithms. So here I'm comparing the number of rounds taken relative to the lower bound, right? I don't know what the optimum solution is, but I'm just comparing to the lower bounds that we were able to compute as the algorithms ran. And in fact, if you look at this weighted matching algorithm, so we have to sort of add some notion of weights which talk about when some item has a bigger target set, maybe I should do this transfer before some other transfer. So we add some weights there. But this weighted matching algorithm, which is shown in pink, as you see, comes very, very close to the, so in these runs it actually gave an optimal solution. But in general, it was sort of a very good algorithm. And here is sort of the bound of our approximation algorithm. So this is a slight variant of the algorithm that I described, the one in yellow. And so in some runs it did extremely well, matching or coming very close to the matching algorithm. But in some examples it did a bit worse. So here the algorithm was within 2 times the optimum solution and so on. So as you can see, it's not as bad as a 9.5 bound. In fact, the worst example we have for the algorithm is roughly like a 3. So we know that our algorithm doesn't do better than a 3 approximation, right? Because there are examples where it does as badly as 3. And the upper bound is something like 9.5. And there are other newer algorithms that we have that are a bit more complicated, but they get a bound of 6.5. So that's sort of the best bound. So this is the same worst case example that I talked about earlier, which talked about the difficulty of finding lower bounds. And for the matching based algorithm, actually this thing does very badly on this kind of situation where the target sets are all disjoint here, right? So this group wants something, this group wants something, and so on. But whatever all these groups want is all shared among a small common set of disks. In this case, the matching algorithm does pretty badly. Okay, so this might be a good. I wanted to give you all the references. So the 9.5 algorithm that I talked about, that's a paper that was published a couple of years ago in Siam Journal of Computing. And then we implemented different algorithms and different heuristics, and that was an experimental paper essentially that was published in ESA 2004, which is called Data Migration on Parallel Disks. And the first problem that I talked about, the data layout problem, we're just trying to find an initial layout, was a paper from SORA 2000, which was joint work with Liana Golubchik, Sanjeev Khanna, Thurimella and Zhu. And then with a PhD student, Srinivas Kashyap, I also worked on the layout problem where we were looking at how to design layout algorithms where the data objects did not all have size 1. So the movies may have had different sizes, and how do you now find a layout for different size objects? And we have certain bounds when the data objects themselves may be non-uniform in terms of their size. There is a paper again that's going to appear in Journal of Algorithms next month. And then there are certain improved bounds that we had for certain special cases, because these data migration problems, if you think about it, actually generalize the traditional gossiping and broadcasting problem. So gossiping is a problem where it's a special case of data migration where there are n people, everybody has something to tell everybody else. And in every round you can essentially, there's a telephone call model which says that you can set up phone calls between any pair of individuals, and either they can send one item to another person or they can send everything they know. There are 2 different submodels there. And broadcasting is just a simple case where only one person has something that they want to communicate to everybody else. So we looked at special cases like single source multicast. Here, one server has a whole bunch of items which it wants to multicast to different people. So the set of the target sets now could be arbitrary, but there's one source that has everything. In fact, in this case, the algorithm that we developed, which is a completely different algorithm from the one I described, gives you a bound of opt plus delta. Delta is simply the number of items. And then we looked at multi-source broadcast where the sources are all distinct, but then you want to broadcast the data. And in fact, that gives us a bound of opt plus 3, and so on. So certain special cases all have improved algorithms. So let me close with sort of one question and a direction that seems very promising, and we've only done experimental work on that so far, but we don't have any theorems to show. So you might ask, well, in setting up the whole data migration problem, we assume that you have an existing layout, and then somebody tells you, well, this layout isn't very good. The demand is not what we thought it was going to be when you chose the layout. The new demand is very different. We're assuming that we just use the new demand pattern to find some new target layout and say, convert this layout to that layout. But one might ask is that, well, how did we choose the target layout? Maybe there were hundreds of layouts that were all equally good in terms of performance, But some of them I could convert my existing layout to very quickly. Whereas if I just randomly chose one layout and said, move to this layout, maybe you are satisfying 95% of the demand and you're spending 50 rounds to do that. But I could actually find other layouts where I could also satisfy 95% of the demand and only use 3 rounds. And in fact, experimentally, we found that to be the case. So when the demand pattern changes slightly, what happens is the sliding window algorithm, for example, reorders the items on the list and comes up perhaps with a fairly different layout than what we had. But nothing fundamentally changed. All the demands changed very slightly. So in one round, you could have actually found a new layout which was as good as the target layout. So we've been looking at that problem where I'm trying to optimize now over the space of target layouts. And at least experimentally, it seems that that is true. So we have some heuristics that start off from the existing layout and use the new demand to find a new layout as opposed to just picking one arbitrarily and saying, let's move there. Okay? But I cannot have proved to you things like, what we would like to be able to prove is that if I give you some budget on how many transfer rounds you're allowed, then I can come as close to optimal by some function of that target number of rounds. Okay, so let's get into the topic. Questions? Question, yeah.
So here you were ignoring the capacity in the sense that while you are doing the migration, disks are storing more stuff than the capacity.
Yes, that's right.
So what is known in the case when you don't allow inflation of capacity?
So it's like a temporary inflation of capacity, right? Nothing that so the paper by Carlin actually addresses that. So they assume in their model that each disk has one temporary extra unit of storage capacity. And their schedule takes that constraint into account. But of course it's working with a specific transfer graph which makes the problem a lot easier. So essentially what's happening is that edge coloring would be one way to solve the problem once you have a fixed transfer graph. The only difficulty is the following. So suppose this guy has 2 edges in and 2 edges out. That's a disk. So it has initially, let's say, items A and B, and it wants to send A there and B there, and it's expected to get new items C and D, right? What you don't want to happen is that both C arrives, B arrives, and then A and B leave later on, right? So when you find an edge coloring, you have no control over what colors these things get. So what they assume in their paper is that there's sort of one extra unit of storage available at this disk. So their schedule, valid schedules would be C comes in, then A goes out, then D comes in, then B goes out, right? They would not allow for C and D to be transferred in first. And the way they essentially do that is they take this directed graph, rather than finding an edge coloring, you sort of want to, say, take an Euler tour of this graph and then schedule those transfers, because that will alternate the in and out edges. So you'll move something in and something out, and then take another Euler tour. So you're kind of decomposing the graph by using this idea of stripping off Euler tours and then doing the transfers along each of those. Yes?
In some kind of a practical environment like
Yes.
a peer-to-peer network or
Yes.
something, you could imagine that the global demand curves might
Not
not
known.
actually be known.
That's right. This is for a centralized disk system where somebody has 100 devices and they're trying to control them, and they can say move this data here and move this data there, not in the terms of peer-to-peer systems where people don't even know everybody else in the system.
All you know is your local
That's right.
demand or
That's
something.
So certainly none of our results would apply to that model. It would only apply to a localized framework where some centralized controller can control who stores what. For sure.
Do you have any thoughts as to whether the decentralized method is sort of, could it come close to these results?
Not right now. No, I really don't know. But you're absolutely right that eventually we want to be able to address things like that where the system is distributed, no central party can completely control who's storing what, people might decide to leave the system, and when they leave they just leave without warning and things like that, and you still want the data to be available at all times, right?
And to meet whatever
That's right, the demand, that's right. That's right. But there are some interesting pieces of work. I mean, I remember looking at one paper which may be related to the kind of question you're asking, which is by David Kempe at USC, where essentially he's trying to gather statistics in a fault-tolerant way. So even asking the question like, what's a hot item, or what are the 3 most popular items in a distributed setting may not be totally trivial, especially with taking fault tolerance into account. So he has some papers in the last couple of years that try to...
If the objects that I have to store are a lot smaller than my disks, then this problem sort of vanishes, right?
If the size of the object?
Yeah. I mean, I thought...
That would just mean that K is very big, that's all.
Yeah, right. And I'm saying if K is very big, then sort of anything works, right?
I don't know. In a centralized system or?
Centralized solution.
But you want to make sure you still store the more popular items.
I understand, but if you just sort of replicate the more popular items, then the thing that makes this hard is when K is small.
Well, K being small is certainly harder, and even the bound sort of suggests that when K is big, it's almost optimal anyway. And the hard thing is when K is smaller.
My guess is that in practical settings right now, K is pretty big.
It sort of depends on how you define the size of the object as well, right? So.
Right.
Maybe you took your movies and you striped them.
Yeah, so the disk is a logical disk. It doesn't have to be a physical device. So for example, you might say this disk is a cluster of 10 disks, and I've striped the data on that group of 10 disks, and that's fine. So I'm going to just view a disk as a logical device that has a certain load handling capacity and a storage handling capacity. I'm not assuming anything about the physical layout. Each logical disk might be a cluster of disks on which data is striped.
But what if you took your movie and you broke it into 1,000 pieces, and then you would be increasing your K? Then does the problem get easier?
So there was a paper a few years ago, I'm trying to remember, by some systems people where they kind of tried to argue, it's certainly referenced in our SODA 2000 paper, where they tried to argue that striping across the whole system was a bad idea from the fault tolerance perspective. So they suggested that the right framework should be where you have groups of disks and then you stripe within the group as opposed to striping across the whole system. I don't know the details of that work.
Point that is that I can make K big by striping.
By having sub-objects.
Yeah.
That's right. Yeah. I agree, but then what I'm saying is in our view, it doesn't have to be a physical device. It can be, when I say a disk, it's a logical disk, which could be 10 different disks, each storing some amount of data, and the data is striped in that whole group. That's fine.
I suppose you could do a fountain code.
Right, you can use other codes, right. That's right.
Then it's always feasible.
So there's also the per connection overhead, which would increase if you
Right. That's, I guess
break
that's
it into
not
several pieces. So presumably you don't want to do that.
Okay, thank you very much.
Thank you.